Good morning. So, some announcements. Is it possible for you to turn in your homeworks at the end of the recitation tomorrow? I mean, the only reason is that if you turn it in, I can give you the solutions immediately afterwards to study for the exam. If you turn it in on... You have the option. Well, then I can't turn in the solutions because it's just, I don't care. If you want to turn it in on Thursday morning, I can give you the solutions immediately afterwards. So if you guys are agreeable to turning it in the recitation, I can give it to you at the end of the recitation. So, I will have the solutions ready. It's just a matter of I don't want to give it out before the homeworks are in. All right. Think about it, and in the afternoon I'll assess the question. All right. Any questions from last week before I start on what I want to do today? Some things that are not clear that you want clarifications on?
The state space vector.
State price vector. Yes. Okay. So there is one question about the state price vector. Anything else?
Distinguishing the yi's from the vector itself as we have.
Okay. So I'll go over it again. Okay. So there's the last part that we didn't talk about last week, which was this risk-neutral probability measure. So I'll go over the state prices again and then talk about this risk-neutral probability measure. Where is my page? Okay, so here's the story. What I did last week, and I tried to put in a few more clarifications which might make things a little bit clearer, maybe. So here's what is happening. I have translated the story of no arbitrage into saying a statement about this matrix A. What I'm saying is that here is a matrix A, and what is the dimension of this matrix? It has m plus 1 rows and n columns. That's what this matrix lives in. Okay? And what I'm saying, no arbitrage, meaning no type A or type B arbitrage, means the following. That there does not exist, this inverted E means there exists, with a cross over it, I'm saying there does not exist a portfolio theta such that A, or I should maybe make it completely more exact what I'm saying, for each I, no matter which I pick, taking values 1, 2, up through m plus 1, there does not exist a theta such that A times theta is greater than equal to EI. So EI is a vector which lives in Rm plus 1 with the ith component equal to 1 and everything else 0. Right? So this is what I'm saying. No arbitrage means that if I define my matrix A in such a manner that no matter which I pick, no matter which index I pick, for every such index, I cannot find a theta such that A times theta is greater than equal to EI. Meaning, what does EI means? EI means I make $1 in state I. State m plus 1 has been identified with the state 0, the state that I start with on time 0. So I cannot find a theta such that I make at least $1 in state I and at least $0 everywhere else. Okay? So for each theta, now I construct this LP. For each theta, so for each I equals 1, 2, up to m plus 1, I construct this LP. Minimize the 0 vector times theta such that A theta is greater than equal to EI and theta free. So I actually have m plus 1 different linear programs that I'm talking about. For every value of I construct a different linear program. All right? And by this statement, I know that no matter which I pick, all of these linear programs are infeasible. Right? Because I've assumed that there is no arbitrage. which means by duality that its dual program, which is max of yi, now this is a scalar quantity here, just to keep things so that you don't confuse yourself here. This is a scalar. It refers to the ith component of the vector y. And what does it have? Y greater than equal to 0, and that's coming from the fact that this is a, what is it? A sensible constraint, therefore you have a sensible variable. And theta free means A transpose times Y must be equal to 0. This is simply, I've constructed the dual. Now I'm saying that this is infeasible, therefore this dual must either be infeasible or unbounded. But y equal to 0 is certainly feasible. Y equal to 0 is greater than equal to 0, and A transpose the 0 vector is the 0 vector. Therefore we end up getting that this is a feasible linear program, therefore it must be unbounded. Okay? Just to fix ideas here, what is the dimension of y? Just m plus 1. So y lives in Rm plus 1. It has one component for every state. And at this point, I'm just trying to maximize the value that it's giving to the ith state. Question?
Since theta is a portfolio, does theta has to be constrained with non-negative?
Who said that? Why does it have to be non-negative?
Because you said it's a portfolio.
So why can't I short stocks?
Oh, okay.
Portfolio doesn't, a portfolio by definition, it means that only a collection of different assets instead of just one. There's no need for it to be non-negative. Okay? All right, so far everybody's with me? There's no confusion? All I'm saying is I have m plus 1 different linear programs. For each of those I construct a dual. The ith linear program tries to maximize the ith component of the dual variable. It doesn't care about the other components, it only cares about the ith component of the dual variable. All right? This is unbounded. So I'm coming up here. So the dual unbounded for, so this implies, I'm just going to put clear, so for each I, the dual unbounded implies that there exists a y such that A transpose y is equal to 0, y is greater than equal to 0, and the ith component of y is strictly positive. For every value of I can find a vector y. For different values of y, this vector could be different. All I'm claiming is that you give me the index I. Because the dual is unbounded for every such index I can create for you a vector which satisfies the dual constraints and its ith component is strictly positive. I cannot say anything about the other components. Only thing I can say is the ith component is strictly positive. And that's just coming from the fact that this is unbounded. If this dual is unbounded, I must be able to find a vector whose ith component is strictly positive. Otherwise, I know that the bound of this is 0. That's not possible, therefore I must find such a vector. Now what I'm doing is I'm labeling, for every y, I'm just labeling this vector that I created by putting a superscript I to it. I'm just attaching a superscript saying that this particular vector is associated with the dual that I created for the ith point, right? So superscript I does not refer to components, it just refers to an entire vector. It is that vector which is coming from the dual corresponding to the ith index. Is this stuff clear? Okay. Now what I'm doing is I'm creating a composite vector from this. Now I'm going to create a vector y which just sums up all of these vectors. I going from 1 through m of y superscript I. So this vector belongs to Rm plus 1. It's an m plus 1 dimensional vector because each of these yi's were m plus 1 dimensional vectors. All right? Now let's look at the ith component of this vector. Y sub I, this means the ith component of y. What can you say about that? It's strictly greater than 0, right? Because I've added up these vectors, which guarantee me that for the ith vector, the ith component is strictly positive. I've summed up, the summation goes from 1 through m plus 1. I've summed up all of them, which guarantees me that every component is positive. So this is strictly positive. And what else? I also know that A transpose times Y, what is the value of this? 0. Each of the yi's, A transpose Y superscript I was 0. I add them up, I still get 0. Therefore, this Y is dual feasible. I'm now going to define a new vector pi. So what does this Y vector look like? It has got components Y1 up through Ym and another component Ym plus 1 because it lives in m plus 1 dimensions. All right? Now I'm going to define a vector pi where I take the m plus first component, take it out, and divide out the rest of the components by that m plus 1th component, and call that my vector pi. Because I want to eventually divide by m plus 1, this is why I went through this entire exercise of trying to show that there exists a vector y whose all the components are positive. Otherwise, I didn't need to. If I just wanted to show a pi which was non-negative, not strictly positive, then I could have done it much simpler. And as an exercise, you might want to think to yourself how you would do it. How would you do this problem if all I cared about was that pi was not a strictly positive vector, but just a non-negative vector?
Just solve the m plus 1 problem.
You just solve the m plus 1 problem, one m plus 1th problem, and that will do it for you. Here I'm going through this entire story because I want each of the components to be positive, strictly positive. And just to look ahead, why do I care about all of them being strictly positive as opposed to just non-negative?
By definition, P is strictly positive.
Which one?
By definition, P is strictly positive.
Right. Okay, let's say, suppose I change the definition of state price vector, just to say that a state price vector has to be non-negative. What will go wrong? Let's just shake that definition. I mean, to some extent, we define things because we need to use them somewhere. And I can change the definition. My life becomes infinitely harder here because of that definition which says it should be strictly positive. Unless I need that strictly positive, I might as well just relax it to non-negative and work with that. What will happen if I don't keep it non-negative? So,
All zeros?
I mean, that might have to do with the probability of say happening.
well, not yet, right? Not yet. Anyway, think about it. For the purposes of this class, we don't really care about it. In FE1, we'll come and re-talk about why do we need strictly positive. Here, we're just trying to use this as an exercise in duality to show that that definition will work. Question?
Does it guarantee that pi is unique?
No, it does not guarantee the pi you're using. Whether you put strict positivity or not, this pi is not unique. Like right now, we are working with the definition that pi is strictly positive, but all I'm claiming here is there exists a y which is greater than 0. The entire construction, you cannot guarantee that this pi is unique. Right? Okay. So for now, let's just say that this is how I define my pi. Because the ith component is positive, I know that this pi vector is a strictly positive vector. This pen has died. So this guy is strictly positive. And what else can I say? I can say that, let's go over here. I don't need this dual. So A transpose times Y, if I expand this out, ends up having S1 transpose the first m components minus S0 times the m plus 1th component. This is what this A transpose Y would look like if you expand out what it stands for. This is equal to 0. If I divide out by m plus 1, ym plus 1, this implies that S1 transpose this vector, 1 over m plus 1 times y1 ym is equal to S0. I'm just taking that thing over to the other side. and dividing out by ym plus 1 on both sides, and I can do that because ym plus 1 is strictly positive. This, by definition, is my pi vector. So therefore, I end up getting that S0, oh, there shouldn't be a transpose here, because A has been transposed. So this implies that S0 is equal to S1 pi. All right. So I've created a strictly positive vector pi which satisfies this condition. And what does this condition mean? It means that the current prices for all the n basic securities that I started with is exactly equal to the prices tomorrow in the next period multiplied by the vector pi. The state prices are pi. And what this is saying is that if you multiply the payoffs in the states with their state prices, you get the price that you pay today. All right? Any questions? Yes.
So in problem 4,
Yes.
instead of doing the first line in program with all the thetas, we can just do this and...
Yeah. So if you want to show no arbitrage, there are two ways of doing it. One way of doing it is solving m plus 1 different linear programs that we did. Another way of doing it is to ensure that pi is strictly positive. Now the question is, how do you construct one linear program that would make sure that if there exists a pi which is strictly positive, it will find it? So now we have shown, so in the part 4, or what is question 4, you've been asked to show that the set of prices that are given to you have no arbitrage. So one possibility is to solve, 21 different linear programs, because you've got 20 different states plus the state at 0, which gives you m plus 1 equal to 21, and show that each of them is unbounded or infeasible. Another possibility is to show that there exists a pi, a vector pi, which is strictly positive for each of the components. Now the question is that if you solve a linear program, how do you ensure that if there exists such a pi, it will find that? If you simply maximize some objective, you're not guaranteed that every component is going to be positive. That's basically what you have to do in that problem. Either go through the pain of solving 21 linear programs, or go through the pain of figuring out how to find this one linear program that will do the trick. Okay? All right. Question?
If we find a pi that is strictly positive,
Yes?
how does it imply that there is no arbitrage possible?
Okay. Work backwards. So what does it mean a strictly, so if you look at the dual, so what was, let's go back, let's see, oh, right here. Okay? So we found a pi which is strictly positive. Stick in the vector 1 at the bottom, at the n plus 1th component. Right? That will be feasible for this. Right? Because just by definition, the way we have constructed it, pi followed by the 1 vector at the n plus 1 position is feasible for this. Now I know that that is strictly positive. For each of those components, it's greater than 0, strictly greater than 0. But if I multiply that pi, this pi followed by the 1, by any non-negative number, any positive number, that is still feasible. Right? For any positive number, that pi is still feasible here, which means that this dual linear program is unbounded. By strong duality, it means that this primal linear program must be infeasible. There's nothing else it can do. Right? And therefore, it means that for every I, there doesn't exist a theta for which you can find an arbitrage. And this is where things start to fail. When you have pi which is restricted to be just non-negative as opposed to positive. Because if it's non-negative, you're not guaranteed that there could be a component I which is 0, which would mean that this is feasible. Okay? But the only sort of confusing issue is that things become problematic if the market is incomplete. So even if this is 0, it doesn't necessarily mean that there is an arbitrage opportunity unless some other things happen. So all kinds of problems happen if you allow pi to be non-negative as opposed to strictly positive. To avoid all of those problems, let's just make it strictly positive. Because whenever there is no arbitrage, I can find such a pi. So why bother with unnecessarily causing ourselves problem later on? Okay. All right. Any questions? Any other questions?
How does it come into application?
Oh,
S not equal to S1 pi.
Okay, this, so right now, how does this come into an application? Good question. The problem 4b that you're doing in the homework that's due on Tuesday, or Thursday rather, or if I would like it on Wednesday, then you can do that last part in two different ways. You can either construct a primal linear program, which is possibly the most logical way of doing it, or you can construct the dual linear program. When you construct the dual linear program, this will be the constraint that you will get. You can pretend as if there are two things happening. You can pretend as if pi are the legitimate prices for tomorrow's states. I don't know which of these pi's will occur, but for tomorrow's states, any pi that is legitimate must satisfy this constraint. It must be strictly positive, and it must satisfy this. That are all possible price vectors that I can use for tomorrow. And if I'm trying to price something today, I can look at what are the legitimate prices tomorrow and then price today according to what happens tomorrow. That's the physical field for this pi. But if you solve the problem without looking at the dual, this pi will never appear and you wouldn't see what is happening. But it will appear in sensitivity analysis. So if you look through the sensitivity analysis of that problem, for which you have to do in order to get the prices for these two different options, essentially what you're doing is finding a pi. The dual variables are, the sensitivity vectors are basically the dual variables, so you are implicitly computing the pi's that will price tomorrow. Okay? All right. So the last step that I want to do about this story is this thing about a numeraire, which makes things look a little bit nicer. So far, what is our story? We are assuming that the market has no arbitrage. So no arbitrage implies that there exists a pi which is strictly positive, such that the price today is simply the price tomorrow multiplied by the state prices. Right? This is what no arbitrage means. Now I'm assuming that there exists a numeraire. And the numeraire is just a security, which means a numeraire is a security such that its price, let's say S0, what do I use for there? N. So S0N is strictly positive. If N is the numeraire, let's call the nth security the numeraire, then I'm assuming that its price today is positive, and its price tomorrow in any state of the world, how do I want to do this? Yeah, so there is this should have been an N here, not a J. So its price tomorrow in any state of the world J is strictly positive. This is by definition the meaning of a numeraire. A numeraire simply means it's a security whose price is never zero. It's strictly positive. And what I'm doing is I'm starting off from this definition of state price vectors, dividing by various quantities, and I end up getting something that looks a little nicer. So I start from this equation. So this equation implies that for every J, that's what that inverted V stands for every J, the price of the jth security today, which is S0J, is equal to the price of the jth security in some state omega I times its state price vector pi I taking values 1 through m. There are m possible states tomorrow. They all have their state price vector associated with them. Take the price of the jth security in that state, multiplied by its state price vector, add it up, it's equal to the price that you'll pay today. Okay? Now what I'm doing is I'm dividing this by S0N. So S0J divided by S0N. And this is allowed because I've assumed that the numeraire is a strictly positive price. So I can divide things. So here I'm doing same thing, I going from 1 through m, as j of omega I pi I. And at the bottom I'm just using a different index. K going from 1 through m of Sn omega k pi k. Alright, I'm just doing the same thing in the bottom and the top. Numerator and denominator, I'm just writing the same expression, the numerator for the jth security and the denominator for the nth security. That's what there is a typo. This should have been n rather than j. Okay? Now what do? I multiply and divide things. So what I'm trying to figure out is that this is the expression I'm after. The price of the jth security divided by the price of the nth security. This is what happens at time 0. Now I want to get the same thing to happen at time 1. So I multiply and divide. So I can write this expression as the following. Sum over I going from 1 through m Sj of omega I divided by Sn of omega I times Sn of omega I pi I. Right? I just multiplied and divided by Sn of omega I. The denominator I'm going to write back again. So far all I'm doing is I took the numerator, which was this expression, Sj of omega I times pi I. And I divided by Sn of omega I and multiplied by Sn of omega I. Nothing happened. These two will cancel, I'll get back the same thing. But I'm allowed to do this because I know that Sn of omega I is strictly positive. And then now I divide by the the denominator, which is k going from 1 through m of Sn of omega k pi k. All right? Okay. Now I'm going to take these two terms. There is one term here. Let's use a green thing. So this is one term, and this is the other term. I'm just going to sum them in different orders. I'm just going to take one of them and put it as a different quantity and then multiply with the other one. So here's what I'm doing. I'm taking this term, Sn of omega I times pi I, divided by, at the bottom, I just have a summation. So I just divide out by the entire summation. This is probably completely off, so I'm just going to move it laterally. So from here, I'm coming over there. So I'm taking the sum from I going from 1 through m. This is the summation at the top. I'm keeping that summation, except that I'm going to sum things in different orders. First term, I'm going to take Sn of omega I times pi I, divided by the entire summation, sum over k going from 1 through m, Sn of omega k times pi k. And multiply this by this ratio, which is Sj of omega I divided by Sn of omega I. Right? So far nothing has happened. I started from this initial expression. The information that's there here is the same that is here, is the same that is here, and it's the same that is here. All right? It's just, I've gone through this gymnastics for a reason. But so far, whatever is information, so the thing that you should keep in mind is that although this looks like it's fancier, it has no more information than saying that there exists a positive state price vector. It's just convenient to think of it in a slightly different way. I'm going to define this fellow, this entire thing, as the vector, as a component qi. I'm just going to call that entire bracket, whatever is in that bracket, as qi. What can I say about qi? Pi I is strictly positive. By the definition of the numeraire, Sn is strictly positive. So I know that qi is strictly positive. Anything else about qi? Less than 1? Sums up to 1. Stronger than less than 1. So it's less than 1, but you can say something stronger, which is that if you sum up all the qi's, I going from 1 through m plus 1, or not m plus 1, just m, they sum equal to 1. These two statements imply that Q is a probability mass function. It's some arbitrary probability mass function. I've just created this probability mass function by looking at the dual variables. Now if you think of that as a probability mass function, so let's write out this expression again. So what is that expression there? All it's saying, let's remove this. So what does this whole big expression now look like? It's just I going from 1 through m, qi times sj of omega I divided by Sn of omega I. That's what that expression boils down to. I've just replaced that ugly looking bracket by Qi. Now what is the interpretation of this guy? What is it doing? If Q is a probability mass function, what is this expression?
It's an expectation.
It's an expectation of what?
Under the probability mass function of the
Expectation of the profit which we get at
the payoff.
payoff in the last.
So it's the expectation of let's see how do I write here? So typically what people talk about are something called deflated prices. So you think of this particular price or this particular payoff as being deflated by the price of the numeraire. So what this expression says, if you compare this expression, so this expression is equal to this expression going through this entire cycle. So what it's saying is that if you look at the deflated prices today, then they are exactly equal to the expected value of the deflated prices tomorrow. Or discounted prices. So the Sn, if Sn is an interest rate, if it's a profit, if it is the numeraire is a bond that pays a fixed amount in all the states tomorrow, then this is indeed the discounted prices. If Sn is not a bond, then it may not be discounted. Okay? So at the end of the day, all we are saying is that if I take my state price vector, which is strictly positive, and I'm given a numeraire which is strictly positive prices, then I can construct a probability measure such that the prices today, discounted or deflated by the numeraire, is exactly equal to the prices tomorrow deflated by the numeraire. So taking it one step up, this is the same thing as saying that S0j divided by S0n is equal to the expected value, did I use a superscript? Yes, under Q of the random variable Sj of omega divided by Sn of omega. I don't know which state omega I would be given. Therefore, this ratio is a random variable. Depending upon which state appears, I get a different payoff. I'm pretending as if this random variable is distributed according to the probability measure Q. Then this exactly holds. Now, in the stochastic processes course, have you guys talked about martingales at all? Not yet. Planning to. Okay. So when you come to martingales, what you will see is that they will define a stochastic process as a martingale if, given the information today, the value of that stochastic process is exactly equal to the expected value that you will get tomorrow. If the value of a stochastic process today is exactly equal to the expected value of that stochastic process tomorrow, given the information today, there are two things happening here. You've got a stochastic process that goes along. These prices are stochastic processes. They are living forever. I'm sitting today and I'm looking at this. What is my information today? My information today, where did my picture go over there? Vanished somewhere. So here's I'm sitting here today. And given my information today, I know that it can appear anywhere in one of these m states. And what this expression says is that given that information, the expected value under Q of what happens to this stochastic process tomorrow is exactly equal to what it is today. Okay? So that's what a martingale is. Now, for those of you who have seen martingales before, let's ask a question. And this would go back to the question that was raised earlier in the class. What if I restrict my trading to be non-negative? So when I was constructing these arbitrages, the arbitrage LPs, I was saying that my theta is free. It is allowed to take any variable. Now suppose, let's put some constraints on it. Let's say that theta is restricted to be non-negative. I can only hold long positions in the stock. I cannot short it. Then what can you say would happen to the security prices? If everybody in the market can only hold long positions and there is some government that's giving you out, that's issuing stocks, what can you say here? For those of you who have taken stochastic processes, you should be able to just tell me straight out what will happen here. Under Q, the security prices would be what kind of a process? Well, unbounded in both cases, right? In some sense. I mean, both cases there is unbounded. But what is something special? So if you intuitively think about this, what is happening? When something is a martingale, it means that if you put in a portfolio today, look at its expected value tomorrow, you don't lose anything. Because the expected value is the same. And therefore, if you invest in something today, and you look at its value tomorrow, you don't lose anything. Go after that, you don't lose anything. Now if somebody told you that you're restricted from choosing all possible portfolios, somebody tells you you can't choose this nice portfolio that you really wanted to, then what do you expect should happen?
Should be below
So this would be above or below? You will lose money tomorrow. So today it's more than tomorrow. So this is what you will get today. So if this expected value is greater than this expected value, it means that in expectation, I expect to make money tomorrow. So anyway, think about it. This is not relevant for this class. You'll probably get to in the stochastic processes, you'll get to these processes called sub and super martingales, and this will show up there. Those of you who would go on to do, not those of you, all of you will go on to do FE2. There you will show up, this same story will show up when you're trying to do American option pricing. There's a stopping time problem, and if you correctly solve the stopping time problem, you get a martingale. If you don't correctly solve the stopping time problem, that you end up getting a different process, which is not a martingale. So in effect, you can lose money. If you do the optimum thing, you don't lose money. If you do something suboptimum, you lose money. And that can be translated into a definition of these processes. I'm trying to remember, there is actually a book, which I've forgotten the title and also the authors, which talks about all of these in terms of gambling. There's this book which is all about gambling. How do you gamble? And all these ideas of super and sub martingales and martingales themselves, they prove everything in terms of gambling. It's an interesting read. Not very mathematically deep, but it's fun to read. Okay, so this discussion closes whatever I want to talk about linear programming. So tomorrow, the recitation, Ali would not be there, so I'll be taking on the recitation. So from now until tomorrow, please try to review whatever you want to know about linear programming, and we'll talk about it again tomorrow. What time is it? Plenty of time. Any questions for just what we talked about right now before I go on to the next topic?
So like you said that whatever value is there today,
Yes.
it's the same as the expected value tomorrow.
Yes.
So how do people earn money and work? If the value is the same,
Yes.
why would somebody invest? What's the point?
Okay. Here's so the question asked was that if the expected value tomorrow is the same as the expected value today, why bother? Just put it in the bank and then you can relax. There's no risk. Okay, so that question can be answered in many ways. First thing is that all of this discussion simply says that there exists a Q. It doesn't say that this Q is unique. Nothing here says that this Q is unique. Different people might think that different Qs will happen. A trading will happen in the market because different people have different subjective things about what's going to happen tomorrow, or interest in different states. Some people are interested in state M+1. Somebody has issued some kind of liability that matures only in state M. Some other person has some liabilities or has incomes available in state 1, and they want to move things around. So they want to be able to trade such that both their risk comes down. If markets are complete, then you can ask the same question, in which case Q becomes unique, and then there is an issue of why would anybody trade? The answer to that question is, the way people get out of that mess is to say that this Q happened because people traded. It's a reverse argument. It's not that the Q exists out there somewhere in the world. It's because people are trading and they are holding different positions, their expectations come in line, which is the rational expectation theory in economics, and because of that there exists an equilibrium where there is a unique Q. That's how people escape from this argument as why is there trading if everything is the same. Everything is the same because there was trading, not the other way around. Okay?
Is trading a way of finding out those pi values?
Well, okay.
Can we intuitively look at it as...
Okay, at the end of the day, after you've done all this computation, you can go back and say, yes, that pi has that interpretation as if people are putting this price for that particular state. But I'm not sure, and I'm just trying to think about this. So one can pretend as if that you start off a market with nobody knows what pies are and let them trade, and if the market comes to an equilibrium and the market is complete, then you would have found that correct pi. And if you're more interested in learning about this, there's this gentleman named Colin Cameron at Caltech, and who's the other guy? Vernon somebody else. Vernon Jones, who used to be at West Virginia but now somewhere else. He got both of these, I think Vernon got his Nobel Prize 2 years ago with Vernon Smith. Those guys have done experiments where they actually got people into a room, made them play with trades, and tried to see if this thing happens, whether a state price actually emerges out of it. And the argument, at least when Colin Cameron gives his talk, is that it doesn't happen in Caltech, and it does happen in Virginia. And the argument is that you need some people who are not so clever for equilibrium to happen. Somebody has to provide liquidity who's not necessarily the most intelligent person out there.
We used to call people who give bad prices as liquidity providers.
Exactly. So there must be somebody who basically is not trying to maximize things, and then things do equilibrate. Or looking at the same thing, the same story appears when I was doing stuff in electrical engineering. There you have to provide noise to the system. You have to give it some noise so that it can get out of some local points where it can get stuck and move to somewhere else, which is the same thing as providing liquidity, which is not priced correctly. Anything else? Residual probability. I've never heard of that name. Which one? It's called an equivalent probability measure. There's a name called equivalent probability measure. And why is it? So in this particular case where you have finite states, equivalent probability measures really don't have much of a meaning. It just means that the original probability measure, if there was one, was putting strictly positive probabilities in all of them. And this Q that I've constructed also puts strictly positive probabilities in all of them. And if you have such a probability measures, then those probability measures are called equivalent. And when you will do simulation, which will happen in the fall, I believe, you'll end up seeing that if probability measures are not equivalent, then one cannot be used to simulate the other one. And one of the reasons we worry about things being equivalent is that we often don't know what the real probability measure is, and we want to simulate it under that new probability measure, and things will not work if it's not equivalent.
So this doesn't really tell us anything about the real probability of which state is more likely to occur.
No, it does not say anything about what happens tomorrow. Everything is subjective. On the other hand, if the market were complete and there was equilibrium, then you might as well pretend that everything happens according to this probability measure. Because why do I care about, so what do I care about tomorrow? I just care about how are the various things priced. Are they priced correctly or not? I'm just looking at the value to what happens to my portfolio. And if this Q is unique, it means that this pi is unique. And if pi is unique, you might as well just assume that the world tomorrow happens according to Q. I don't care about anything else. Okay? Any other questions?
So Phi is also the state price deflator.
Yes, state price vector, deflator,
Different names.
same thing. I mean, to me, I remember it as a dual variable for the constraint, and that's about it. These names can become a bit confusing. All right. So now let's go over to, I have half an hour, so that's good. So now we'll leave the story of linear programming and try to go into nonlinear programming. And music. So before we even go into it, let me tell you something that happens in nonlinear programs. Linear programs are very nice. There is a standard algorithm that will solve all linear programs. No matter what linear program you give me, simplex will solve it. For some linear programs, it will take longer than others, but for all of them, they will find a solution. Nonlinear programs are dirty. You cannot, one algorithm will not solve everything. It's just not possible. In linear programs, we never even talked about local optimality. Question?
I have one question about, it's slightly related to this.
Yeah.
But do you have a constraint that has an absolute value? It's not in the objective function, but it's just a constraint that says absolute value of something has to equal something?
Yes.
That's not a linear program, right?
No.
Okay.
Yes, and we'll come to it when we talk about convex programming in a moment. So the question was, if you had a constraint absolute value equal to beta, let's say beta is a scalar, then that is not a linear program. On the other hand, if you had a constraint absolute value is less than equal to beta, then it is a linear program. So at times, when it comes up in applications, you should try to see the following. If it so happens, let's pretend that you relax the constraint to be absolute value less than equal to beta, and you can convince yourself that in the optimum solution, this constraint will be tight, because this is coming out of some resources. Those resources are very valuable, and you know that in trying to maximize revenue, that constraint will become tight. Then you might as well pretend that it's actually less than equal to beta, solve it as a linear program, because you're guaranteed that at optimality you will get equality, rather than converting it into a nonlinear program, which is a pain. So as long as possible, try to leave it linear. Question?
You says the resource is very valuable, so it's better off if we use the less of that instead of we set the constraint to be.
Well, okay. That just seems like a statement which doesn't make any. I mean, your question doesn't have any relevance to this discussion right now, because all I'm trying to say is that if the constraints are tight, for whatever reason, then you get the story that you can solve it as a linear program. If it doesn't, then you can't. Okay? All right. What else? Okay, so going back to the story of nonlinear programming, one of the reasons why nonlinear programming is often ignored and people don't, it becomes a difficult topic is because everything has to be solved case by case. There isn't one algorithm that will solve everything. And so what we do is tell you various kinds of nonlinear programs that are interesting. We get different types of nonlinear programs, tell you, okay, if you are seeing something like this, use this method. If you're seeing something else, use the other method. It's not, I can't give you one algorithm. And therefore, we will go through a number of different cases, the most important ones, and then ignore the rest. In order to solve these nonlinear programs, typically what one does is try to compute first and second order conditions for optimality in constrained problems. Without the constraints, we solve this problem where in the very beginning, in the first or the second class. We talked about first and second order conditions for optimality for unconstrained nonlinear programs. Now we want to talk about what happens when there are constraints and how can we use that to get an algorithm to solve it. Along the way of trying to define those conditions, we'll get to Lagrange methods. Okay, so here's just what does a nonlinear program look like? This is what it is. It's minimizing or maximizing a nonlinear function f of x such that you've got some inequality constraints going greater than equal to, some of them going less than equal to, and some of them are equal to. Typically the variable x is continuous. Unless otherwise stated, We will assume that in a nonlinear program, the variable can take continuous values. There is no discreteness there. Just to fix ideas, when we talk about nonlinear programs, we did talk about unconstrained nonlinear programs. We did talk about, in the very beginning of class, we talked about nonlinear programs, we talked about unconstrained ones. Why didn't we talk about unconstrained linear programs? Yes?
They're unbounded.
Yeah, they're uninteresting. They're either unbounded or every point has the same value. Either it's flat, so that no matter which decision you do, you get the same payoff. If it's tilted, if the linear function has any tilt, it just goes off to infinity. Plus infinity or minus infinity. Utterly uninteresting. But nonlinear programs don't do that. You can have unconstrained nonlinear programs which are meaningful. And that's why we do talk about unconstrained problems. The other thing that, the reason we do talk about unconstrained problems is that, let's go over one step further. I told you all of this story anyway. So one of the reasons why we did talk about unconstrained problem is typically the way we solve nonlinear programs is we look at a current point, we look at all constraints that are tight at that point and dualize them. We just get rid of those. Now everything that's left over has a lot of slack. And if it's got a slack, it's as if locally the point is unconstrained. It can move in any direction. And therefore, we typically talk about unconstrained problems because we'll end up using them in defining solutions to constrained problems. Okay. The first special case that we will talk about is that of a convex program. But before we get to convex programs, we have to talk about what a convex set is. Okay, so we'll call a set S convex if it has the following property. You take any x and y in S. Take 2 points in S. So here's my set S. What I'm claiming is that I want to pick any 2 arbitrary points in the set S, then the entire line segment x, y, this is the line that joins x to y, is a subset of S. So for every x and y in S, this line segment is in S. If that happens, I'll call the set S convex. The expression that's written over here is simply an algebraic way of writing the same statement. If you take any lambda between 0 and 1, if you take lambda equal to 0 and you plug it into the expression, you end up getting x. If you put lambda equal to 1 in this expression, you end up getting y. For any lambda between 0 and 1, you're taking a weighted combinations of the vector x and the vector y, which is simply spanning out the entire line segment as you go from lambda equal to 0, which is x, to lambda equal to 1, which is y. So is this set convex? No. Why? I can find an x here and a y there. So here's my vector x, here's my y. I join the line segment, it pops out of the set. So this statement must hold for every x and y, not just for a given x and y. No matter which x and y I pick in that set, I must have that x is, that the line joining x and y belongs to the set. Okay, now let's look at some example. Let's define the set S to be this. The vector is x such that A transpose x is less than or equal to B. So A and B, A is a vector which is fixed and given, B is a scalar that's fixed and given. So what is that kind of a set? That's a half space. Is this convex? Yes. How do we go about proving it? Take 2 points. So let's take the points to be x1 and x2. So we know that A transpose x1 is less than or equal to B. A transpose x2 is less than or equal to B. Now I want to show that if I take a linear combination of, or convex combination, so this particular combination is called convex because it's taking a non-negative weighted combination of x and a non-negative weighted combination of y, where the weights add up to 1. So I take a vector x, which is 1 minus lambda times x1 plus lambda times x2. And now I compute what happens to A transpose x. Now A transpose x is equal to 1 minus lambda times A transpose x1 plus lambda times A transpose x2. I also know that this lambda guy lies between 0 and 1. Therefore, this quantity here is non-negative and that quantity there is non-negative. If lambda was not restricted between 0 and 1, then this might not be non-negative, and therefore I know that if this is less than equal to b, that is less than equal to b, this entire expression is less than equal to 1 minus lambda times b plus lambda times b, which is equal to b, which implies that x belongs to S. All right? So that's typically how you would go about proving that a particular set is convex. Take 2 points that belong to the set, take a convex combination of those points, call that x, check whether the constraints defining the set S are satisfied by this new point x, and you're done. Okay. What about, now we're going to use a property of convex sets that makes life a little easier. So if I've given a set S1 which is convex and a set S2 which is convex, what can you say about the set S1 intersection S2? Convex. Why? What is, again, how would we prove this just as an exercise? So you start off, I mean, you can use this definition. So you take 2 points that x and y that belongs to S1 intersection S2. This implies that the entire line segment xy belongs to, is a subset of S1, and the entire line segment xy is a subset of S2. Because S1 and S2 are convex, which implies that the entire line segment xy belongs to S1 intersection S2. So we are done. Okay. This property tells us the following thing. Suppose now we had something which looks like this. Ax less than equal to a vector b. So this is a matrix, that's a vector. That is typically what a linear program's feasible set looks like. What is this? This property tells me that that set S is also convex. Why? Because this set S is the same thing as the following. X such that AI transpose X is less than equal to BI, I taking values 1, 2, up through M. If A is assumed to be R M times N and B is assumed to be in Rm. So you have M linear constraints in N variables, then this set is the same as that set, where AI refers to the ith row. And therefore this is nothing but, so this set is nothing but the intersection of I going from 1 through M of X such that AI transpose X is less than equal to BI. And we've proved that this set is convex. Now we use this property to show that the intersection is convex. Right? So for now, let's just say that these are the only 2 basic properties that we need, and then when we need more things about convex set, we'll come back and redefine it. So the things that I want you to remember is, anytime I say that a set S is convex, it means this. Take any 2 points, the line segment belongs to it. We care about convexity because typically when we try to solve problems, we start from a point and you want to go to another point. And we want to assure ourselves that as we go along this, I won't drop out of it. If the feasible set is convex, I know that if I'm going through this entire line segment, I'll never lose it. I will be in the set. And because of this, there are some other very nice properties that happen when we need it. I'll define those properties. Okay. Once that we have defined what a convex set is, next thing I want to define a convex function. So we will call a function f a nonlinear, or let's say a general function f that takes points in Rn and maps them to points in R, a convex function, if and only if the following thing happens. You take a point, I'll tell you geometrically and then I'll write out the expression, which is that expression down there. So what is happening is, let's just talk about a function from R1 to R1. So here's my function, f of x. What I do is I take some point x1. Let's call it, I think the definition is in x and y, so let's call it x and y. So take a point x and say take a point y. So look at their function values. So here's the function value f of x, there's the function value f of y. Join those function values by a straight line. So here's the straight line that joins them. We will call a function f convex if it so happens that no matter which point I pick, which 2 points I pick, x and y, if I look at their function values and I join the straight line joining them, I end up getting that that straight line lies above the function. So this is not a convex function. This is a convex function. So here's x again. I take any 2 points here, x, take another point y, I join the straight line, it lies above the function. So algebraically, here's how it works. Take any take x and y and take lambda in the interval 0 to 1, then I must have that the function value at any point in the line segment, which is lambda x plus 1 minus lambda y, is less than equal to lambda f of x plus 1 minus lambda f of y. What is this algebraic statement saying? It's saying that as you crank up your lambda from 0 to 1, you are mapping out all points from y to x. Just written it the other way around. This is the function value at some point in the line segment joining x and y, somewhere here. So this point here could be 1 minus lambda times y plus lambda times x. This point here is 1 minus lambda times f of y plus lambda times f of x. That is a point that's on the line segment joining f of x to f of y. This is a point that lies in the line segment joining x to y. And what this statement here says is that if you evaluate the function value at some point in that line segment, it must be less than equal to the function that is predicted by the straight line joining fx and fy. That is the definition of what a convex function is. Now, another way of thinking about convex functions, which may or may not be useful, but at least in convex analysis is very useful, is that really there is no distinction between convex sets and convex functions. They're basically one and the same thing. Anytime you're given a convex function, you can pretend that it's really a set in one extra dimension. So if you look at the function values that lie above the values in this set, you can convince yourself if that the function is convex, then this set is convex. If this set is convex, then the function is convex. Check this on this particular thing. If you look at the set that lies above, that set is not convex because you can find 2 points such that if you join the line segment, it comes out of the set. So convex functions and convex sets are really not two different entities. It's the same thing. You just look at it slightly differently and you get a function. If you took it one extra dimension, you get a set. Okay.
So while parabola.
Question?
Yeah. while a parabola may be convex,
Yes.
inverted one may not be convex.
Well, okay. That, I don't know whether it's put up on the board. Good question. So the question was that a parabola is convex. This is sort of looks like a parabola. It's not quite a parabola. That's convex. An inverted parabola is not convex, but it still has this property that if I correctly define the set, I get a convex set out of it, which is instead of looking at the points above the function, now I have to look at the points below the function. And since that's also convenient for us, we will call a function f from Rn to R concave if and only if the negative of the function is convex. So instead of just looking at the function, if things got inverted, then geometrically there is still nice properties here. It's still the same properties as if here. If I'm trying to maximize something or minimize something, we can, if you like this function, we should like that function. And if you invert it, you end up getting a different function called concave. The only difference is that instead of looking at the function itself, you'll have to look at the negative of the function. This particular function is neither. It's neither convex nor concave. And again, geometrically what will happen is for a concave function, if you take any 2 points, say this point and that point, join the function values should lie below the function rather than above the function, simply because there is a minus sign here. Okay? All right. So here are the properties. Let's see, what else? What are the things we need to use? Okay. We already talked about the first property. We talked about the property that if the sets are convex, then their intersection is convex. Here are a few things that we would need about convex functions. If a bunch of functions fi are convex, you multiply them by something non-negative and add them up. Take non-negative weights and add up the functions. You end up getting a new function which is also convex. How do you prove it? You basically use this statement. Because the alpha i's are non-negative, if I compute this side, I can still upper bound it by this kind of an expression for each of the fi's. Add them up together, you'll end up getting the right expression on the other side. If a function fi's are convex, then the maximum of these functions is convex. Okay, so here's a picture. This is the picture that I keep in mind. It makes life. When I'm talking about concave and convex functions, I can always never remember whether the max is convex or the min is convex. So just think about linear functions. Here's a function, one function f1. Here's another function f2. I don't know. Here's a third function f3. And if you look at the maximum of these guys, what does this function look like? So it looks like I've screwed up there. So we will ask ourselves whether this is right. So what does the maximum of these three functions look like? It's this function here, right? It comes up to this corner and then it picks up as f3, right? That was this function looks like. And that is what kind of a function? Convex. So I wrote up this thing correctly. So the max of functions are going to be convex. What about if you take the min of them? Concave. But what does that min look like on this picture? It goes along here, then it goes along there, and then it comes down this way. So that's the minimum of those three functions, and that's a concave function. If you take the maximum of functions, you get convex functions. You take the minimum of functions, that you get concave functions. What is a linear function? Is it a convex function or a concave function?
Convex function.
Both. So linear functions are extremely nice.
Is that equivalent to being concave and convex at the same time?
Yes. So linear functions are both convex and concave. They are, by definition, the same.
If this was non-linear,
Yes?
it won't be convex. Right?
No, the statement is true. Statement is true, and here's the picture. So don't using linear functions is not any loss of generality. Here's your function. Here's f of x. Here's f of x. There's f of x. Okay. Three nonlinear functions. So this is, let's call this f1. f2, f3. If you take the maximum of these guys, you end up getting this form, which is certainly convex. If you take the minimum of them, what do you get? What? It's not concave. So what went wrong in that definition? What did I have to make in order to make the minimum concave? Now the linear part was nice because a linear is both a concave function and a convex function. So if you take the maximum of a bunch of convex functions, you get convex function. You take a minimum of a bunch of concave functions, you get a concave function. The same story is true here. If fi is a concave, it means minus of fi is a convex function. Therefore, maximum of minus of fx is a concave function. Convex function. Take the negative out, you'll end up getting that the minimum, if fi is a concave, replace the maximum by a minimum, you get concave. So these nonlinear functions are not concave, and therefore taking their minimum will not give you a concave function. But for a linear function, it will work out. Okay. The next property that we need is this one, which I'm not going to prove, but I'm just going to show you geometrically that it's true. The next property says is that you take a convex function f. Now I'm assuming that the function is both convex and differentiable. So far up to now I didn't need to use the fact that f was differentiable. The pictures that I was drawing was clearly smooth functions, but I didn't have to assume that they were differentiable. If it is differentiable, then a function is convex if it has the following property. Take the function, take a point x. Here's the point f of x. At that point, draw the tangent to this curve. So the tangent to the curve is this line. This is a straight line, and what is the value of this straight line? Any point y on this straight line is given by the value at the point x plus the slope at the point x transpose. Let's call this a new function g of y. Okay, so g of y is a linear function. It's a straight line. It's a tangent. It's a plane. And the expression for g of y is given by this. G of y is equal to f of x plus the slope at the point x, y transpose times y minus x. It's just a multidimensional version of this expression. If you look at one dimension, it will be f of x plus the derivative at the point x times y minus x. First order Taylor series expansion at the point x f of x. This is nothing but the first order Taylor series expansion. And what this says is that here only thing is going one way. I'm saying if the function f of s is convex and differentiable, then the first order Taylor series expansion always lies below the function. So here's the first order Taylor series expansion. The f of x is the function on top. When you look at that, it lies below the function f of x. Is this clear? This is quite helpful for us because of the second property over there. If x star is a local maximum, should have been a minimum. If x star is a local minimum, then x star is a global minimum. Let's prove that statement. It's actually pretty trivial. So here's what is happening. We're looking at unconstrained optimization, and we're given a function f of x. So here's the problem. I want to minimize f of x, x in Rn. We did this problem in the very first week. We found various conditions by which we can find local minimum. So let's call x star is a local minimum. Since this is an unconstrained problem, I know that this implies that the gradient at the point x star is equal to the 0 vector. Otherwise, it cannot be a local minimum. So if you look at the function, now let's take y to be any point. So y is any point in Rn, and then we look at the function value at y. By that result over there, we know that this is greater than equal to the function value at point x star plus the gradient at the point x star transpose y minus x star. Instead of just, I wrote out that expression for x star instead of x. By the fact that x star is a local minimum, I know that this vector is the 0 vector. Therefore, this expression drops out, and I end up getting that f of y is greater than equal to f of x star. So it's a global minimum. So this should have been a minimum rather than a maximum. So convex, the only, or not the only, one of the reasons that we are interested in convex functions is because of this property. Convex programming is very nice. I just somehow create for myself a local minimum. Creating local minimum is easy. I have some gradient conditions to check. If I can't solve for this equation, I can at least try to find a point numerically which will solve that equation. Once I solve that equation, I'm guaranteed that that's it. I can stop. I don't have to worry about anything else. This must be the global minimum. If the function is not convex, then this doesn't work, and I have to start all over again, because the point that I got may not be a point which is globally minimum. Okay? All right. The last one, let's just start in the afternoon. We'll have to go further than this anyway. All right. We'll see you in the afternoon.